Hello, everybody, and welcome to this presentation on multi-cloud serverless deployment with Micronaut and GraalVM. For those of you who don't know who I am, my name is Graham Roche, and I am an architect at Oracle Labs. On the agenda for today, we're going to look at traditional versus modern challenges when it comes to serverless versus traditional applications. We're going to look at the challenges specific to serverless. We're going to do an introduction to Micronaut and what it is, and we're going to do an introduction to GraalVM and cover what that is. And then we're going to deploy some Micronaut applications to Oracle Function, and do lots of demos, and hopefully have a good time. So first of all, let's talk about traditional versus modern architectures. So traditionally, applications have been built to be deployed to a single Java virtual machine in that kind of servlet environment. So as WAR files, for example, so multiple applications were able to share the same virtual machine. And as we move to the cloud, you'll see this transition into a containerized environment where essentially applications are running in individual containers and are controlled by an orchestrator such as Kubernetes or the serverless platform that you're operating on. And this represents a significant shift in how applications are designed and architected. And when you look at traditional tools that are, have been built to run on these traditional architectures, things like Spring, CDI, and so forth, they really make extensive use of techniques that are not great from a memory consumption and startup time perspective. Techniques like reflection, runtime bytecode generation, runtime generated proxies, and dynamic class loading essentially cause significant slowdown in terms of startup. And in the serverless world, in serverless reality, we have frameworks based on reflection, and annotations become fat very quickly, and startup time and cold starts can have a very serious impact on both the cloud billing model in terms of having to allocate more CPU cycles to spin up your serverless application, and also to user responsiveness. If the serverless function is not available quickly, the cold starts can actually have an impact on application usability. We love the programming model that these annotation-based frameworks provide, however, and we tend to live with it. But if you do turn these features off, the drop in productivity is massive. So is there something out there that can provide this balance? In terms of why reflection is a problem, today the JDK is OpenJDK, and it's all on GitHub. You can take a look at the source code, which is available in the OpenJDK organization on GitHub. And if you look at the source code for java.lang.class, you'll notice that reflective metadata is initialized on first access to any constructor, field, or method, and stored in what's called a soft reference. This means that it's not garbage collected until the Java virtual machine is actually low on memory. And it's also an all or nothing deal. So you can't just initialize one field or one method, you get everything. And doing this kind of analysis at runtime can lead to a significant slowdown, and because initializing this reflective data is actually relatively expensive. So in terms of what Micronaut is a new application framework for the Java ecosystem that is focused on these modern architectures like serverless and like microservices. It's also a complete application framework for any type of application, whether anything that has static void main can be built with Micronaut. And also it's a Java annotation processor that computes your framework infrastructure at compilation time. So instead of waiting until runtime to analyze your application, Micronaut essentially hooks into Java C and computes everything it needs to run your application during compilation, meaning when you actually spin up your application, there's a lot less to do, and startup time and memory consumption can be reduced greatly. So in that sense, you can think of Micronaut as essentially build time framework infrastructure. At compilation time, Micronaut will compute everything that traditional frameworks do, things like dependency injection and configuration injection, annotation metadata, aspect-oriented programming proxies such as interceptors and so forth. Bean introspection, so that you can serialize and deserialize objects to JSON, or write them or read them from the database. And everything that makes up the core way a framework works, is computed during the compilation phase, eliminating the need for things like reflection, runtime proxy generation, and dynamic class loading. In terms of what GraalVM is a new virtual machine out of Oracle Labs that is able to, in JIT mode, increase your application throughput between 20 and 30%, and reduce latency. And in addition to that, take a Java application and compute it into a self-contained native binary that is really great for cloud and serverless deployments. This native executable is essentially able to start up in milliseconds, in tens of milliseconds, which compared to starting with the Java virtual machine is significantly faster, and use only a fraction of the memory, which has significant impact in terms of reducing costs in cloud billing models. It also has a truffle language framework that allows you to seamlessly use multiple different languages and libraries together. And for example, you can call JavaScript code from Java or Ruby code from Java or vice versa seamlessly without overhead, which is pretty cool. So it's a full kit with a whole bunch of different things. Do check it out at graalvm.org. Now, in terms of the relationship between Micronaut and GraalVM, and in particular in the native image, are essentially a match made in heaven. Why is that? Because essentially, native image, the way it works in terms of doing what's called a closed world static analysis of your application, works really great. However, if you do anything dynamic in your application, such as using reflection or runtime proxies or dynamic class loading, you need to configure GraalVM and tell it about these usages within your application. Now, if you consider that Micronaut eliminates all instances of reflection, runtime bytecode generation, and dynamic class loading, you can see that using Micronaut and GraalVM means that GraalVM native image has a lot less work to do because there's nothing to configure. Micronaut applications are already ready to be computed into native images, which is a big win. And once you've computed your application into a native image, the startup time of Micronaut is phenomenal. It's down to 20 milliseconds and consuming only 18 megabyte, which is orders of magnitude better than the JIT version of running within the Java virtual machine, with the trade-off of reduced peak performance that you get with AOT. So in addition to that, Micronaut and Oracle Cloud have nice integrations. So Micronaut will automatically detect, for example, the presence of Oracle Cloud when you're running your application within Oracle Cloud. In this sense, this is all about being cloud native. Micronaut is cloud native out of the box. It knows you're running an Oracle Cloud, which means that you can essentially automatically adapt your application to the fact that you're running an Oracle Cloud by, for example, using object store in the cloud and a file system locally, dynamically, based on whether you deploy in the cloud or not. Micronaut will also automatically resolve your authentication details, so such that when you deploy it to the cloud, Micronaut will resolve your authentication and your tenancy and so forth, and make that available to the application. It also integrates very nicely with the Oracle Cloud SDK, so that you can inject any component of the Oracle Cloud SDK into your code, and, for example, make calls to object store or any cloud service that is part of Oracle Cloud. And of course, all of this works within native image, so you can compute your application into a native image, and which significantly reduces your startup time and overall memory consumption, which in the cloud results in efficiencies in terms of billing. So speaking of efficiencies, Micronaut also has great support for Oracle Function, which is a service platform that allows you to deploy completely serverless applications behind API gateways or as a response to events. And you can easily build Oracle functions with Micronaut. You can also compute these Oracle functions into native images, allowing them to be more efficient and start up and exhibit significantly better cold start performance. the Oracle function uses a Docker-based deployment model, and there is a guide on how to get started with Oracle function there. So with that, I'm actually going to start doing a demo of using Oracle function with Micronaut. And so to get started, I'm going to use the Micronaut command line interface to create an application. So Micronaut has a command line interface called MN, which you can install via Homebrew or Chocolati on Windows or Mac ports or manually, or SDK man as well. And it allows you to create applications interactively. So I can drop into here and I can say MN app, and then I can say demo, and I can say features, Oracle function to create my application. So that results in a new directory called demo, which I can see into it. And now I can open this up inside an IDE. Okay, so now let's enter presentation mode so you can see all of this a whole lot better. And here we have my Micronaut application, and you can see that when you create a Micronaut application, it actually generates some example code for you here. I'm actually going to get rid of that because I want to demonstrate a particular use case here, so I'm going to delete that out. But what I'm going to do is I'm going to create a person class, or let's do something different and create a pet. So here's my pet class. And for example, a pet can have a name, and then it can have an age, and we can create a constructor for that, and some getters, like that. And we can make this introspective. So what does introspective mean? Now, as part of Java, there is every framework out there has traditionally used what's called the Java Bean introspector, which is java.beans.introspector, which relies on reflection to dynamically figure out the properties of your domain class of your, in this case, pet, and enable things like serialization, deserialization to JSON or reading and writing to a database. By adding introspective, we tell Micronaut that instead we want to compute at compilation time the ability to do that. So that's why I've added that. Now let's have, for example, a theoretical pet storage class. And this is going to be, you can annotate this with singleton to make it singleton scoped in terms of dependency injection. And what I'm going to use is I'm going to just use a map-based storage where we're going to store pets inside a map. So let's do that and then import the map. And we're going to make it a new concurrent hash map like that. And we're going to add a method to get all the pets like so. And that's just going to do map.values to return the in-memory pets. And we're going to add a method to save a new pet. And you can say that you only want valid pets, for example, using validation. And if you do that, you can come in here, for example, and say that the name should not be blank, and the max age of a pet, for example, should be 20. And we get automatic validation. So we're going to be able to add the ability to save a valid pet. And when you do, you're going to say pet.getName, pet to store it in my concurrent hash map. And then we'll have another method to get hold of a particular pet by name. There we go, map.get, and return the pet. So now let's create a controller, like so. And the controller is going to be mapped to the pets endpoint. And it's going to inject my pet storage, which could actually be backed by a database or something like that. But in this case, it's just an in-memory map. And we're going to expose an endpoint, which is going to list all the pets. Like so. That's going to be pet storage.list, like that. And maybe we expose another endpoint to retrieve a pet by name. like so. And that is going to get hold of a pet by name, like so. Pet storage.get name. There we go. And maybe we at the start of this, we're going to save a couple of pets. Maybe we're going to have, for example, arrays.asList new pet. Dino is going to be 10, and maybe Dolly or something like that. It's going to be 8. And we don't have a method called save. Let's do it this way. Pet storage dot save, like that, and pet storage dot save, like that. There we go. Okay, so we've saved a couple of pets, and so they should be available. And now let's write a test. So let's write a test for this. And we're going to write a test that's going to test that we can invoke my endpoint. So it's going to be a Micronaut test. And we're going to have an interface called test client. That's going to be able to invoke my pet's endpoint, like so. And the pet's endpoint, let's just, for example, list the number of available pets. Okay, so we're going to write a test. That's going to test listing the pets, like so. And it's going to inject my pet client. And now we're going to say assert equal to client.list.size. So if all goes well, if we run this test, it should pass. And it does. So that's my endpoint built, and we have an application here. So it exposes a pet endpoint that lists my different pets. So if we wanted to debug this application, we could modify our logging, but essentially it's ready to go. So how do I deploy this application to our cloud? So the only modification I need to make, and I'm going to cheat a bit and get hold of my tenancy address, like so. And I'm going to come into my build.gradle, and you'll see that down here under the Docker build configuration, we have to configure the target of where we want to deploy this application to. And I'm going to deploy this application to Oracle Cloud. So I'm going to configure my tenancy, the repository, the tenancy ID, and my repository name, like so. And I'm going to do it for both of these. One is the native build and one is the regular build. So just by configuring the image flag of the Docker build, I'm able to configure where I want to deploy to. Okay, so once that's configured, all you have to do is, first of all, log into Docker, which I'm going to do by copying this and logging into my Oracle Cloud account in Oracle Container Registry. And I'm going to do create w docker push. And this is going to build and deploy a Docker image for the JIT version, so the regular Java version. And that's what I'm doing right now. So there you go, deployed. And once I've done that, I'm going to deploy the function. I'm going to use project fn command line. I'm going to say fn.create function demo, and actually I should have captured the output of that image. So this is my image name that I just deployed. So I'm going to do docker.fn create function demo, and the name of the image, like that. And that's going to create a new function that points to the image name that I just deployed. If I then go in a browser to my Oracle console account and log in and go into Developer Services, API Gateway, and then go into my gateway definition. And I'm going to use API Gateway to create a new deployment that is referencing called pets, that is referencing my pets endpoint. So there we go, click next. Then I'm going to just map the whole path to deploy the application, and I'm going to select any method. And I'm going to choose Oracle function as the backing type. I'm going to change my compartment, select my demos compartment, and select the function that I just deployed. Click next, and create my function deployment. So it's creating my function here. And once this may take a few minutes, but once the function is available, it'll be available at this endpoint, which I can copy. You can use curl from that link to essentially send a curl request. And notice how long this takes in terms of executing. So this is accessing the remember, this is accessing the Java version, the JIT version of the function that I just deployed. And it's doing a cold start. So it's starting completely from a cold start, spinning up the function, and you'll notice that the cold start period is significant in terms because it's written in Java, it has to spin up the virtual machine. Now there are ways to improve this cold start performance. You can come into edit and you can essentially edit your function's memory allocation. To allocate more memory in terms of allocating more memory so that Java has more time, more space to operate. The default function executions on Oracle function is 128 megabytes. And you can see, in fact, it timed out. So if I go to, I will have to do that. So if I go to Developer Services here, and then Functions, and go to my function that I deployed. Here it is, edit function. And I'll need to allocate more memory to the Java version. Okay, so run it again. And hopefully this time, with the additional memory allocated to the function, we will see a response, which we do. There we go. So there you go. There's my response from my controller, which I created. Now, as you can see, deploying the Java version required additional memory. The cold start was much longer. So let's take the same application and instead deploy the native version. So I'm going to run docker push native. And this is going to use GraalVM's closed world static analysis to analyze the application and produce a static native binary of the application and push it up to Docker. So this whole process actually takes a little bit of time, and then it has to build the native image. And this is one of the trade-offs when it comes to AOTs. With AOT, you have longer compilation times as it goes through and analyzes all the reachable points in your application and builds out a native executable. The native executable that gets built is also built specifically to target a particular environment. So, for example, you can build a native image in this case, for Linux, the Linux environment that runs on Oracle Cloud, and it will only run on that environment. So the native executable that is built will not run on Windows. It will not run on Mac. It will run only on the Oracle function environment. And due to the fact that it's native, it can optimize how quickly it starts up as it stores essentially the application in native image heap. But as you can see, it's going to do static analysis. It's going to build the application up and parse all the endpoints and understand the construction of the application. And then it's going to build that application into a Docker image and push it into the cloud. Once it's actually built and pushed into the cloud, what we can do is we can alter my function definition through the gateway and instead point to this new native version. And the native version will have significantly better cold start performance than the Java version, thanks to this. You see, it's done building the image, pushing it up, and it's tagged it and created a new function. So what we can do is we can come back to the Oracle Developer Console here, and what we before we do that, actually, we're going to create a new function. So I'm going to say fn create function demo native, which is the native version. We want a native function. Name it something else. There we go. So we've created the native version. Then we're going to come into my gateway and into my gateway definition over here, to my deployment. Here it is. We're going to edit the deployment and the route. And instead of pointing to the demo version, we're going to deploy to the native version, save that out, wait for it to update. And now my function definition and deployment, instead of pointing to the JIT version, is now deploying to the native executable, which if we try out my endpoint, let's just wait for it to update. It takes a little bit of time to update. There we go, it's updated. So now let's go and do my GraalVM and see what happens. There we go, can you see? So as with the native version, there wasn't that long period of waiting around. It started pretty much in under 5 seconds, cold start performance, and exhibits much better cold start performance overall. And you can also go back into the developer services and lower your memory allocation back down to 128 megabyte, and it will still work. Now, if you wanted to deploy this to a different cloud, what you could do is you could come into your build.gradle here and modify the runtime in Micronaut, which is defined here, to a different runtime. For example, I can modify this to NetHeat if you were deploying to a serverless runtime that supported, just exposing containers on port 8080. And if I just comment these 2 lines out for a minute, so that I can just build a local container and build that out. So, and now I can do docker run demo, and now it's running the same application, but instead just exposed over port 8080 without making any changes to the application itself. Just by changing the runtime from Oracle function to NetHeat and exposing it, I can run the same application in a Docker container. Okay, so that was the demo part of the demo part. You can deploy to Oracle function just by logging into container registry, doing GraalW Docker push. You can deploy the native version, which exhibits significantly faster cold start performance using Docker push native. To make the function available, you can use the project fn command line, fn create function, to create the function. And once you have that, the cold start performance from the native version compared to the JIT version is significantly better. In this graph, you can see the native version in blue and the Java version, regular Java version in green. And as you can see, the cold start in the native version is around 4 seconds, whilst the Java version is 40 seconds, 10 times slower for the same memory allocation. You can take the same application as well and deploy it to other cloud platforms just by altering the runtime, like I demonstrated. Modify the runtime, build a Docker image, and you can deploy it to any serverless platform that supports, such as Knative or anything like that, that supports exposing a serverless application in a container exposed over port 8080. So in summary, Micronaut and GraalVM are leading this AOT revolution of using ahead of time compilation to compute a native image that is more efficient and more to start up and in terms of cold starts for serverless. You can easily create and deploy serverless applications with Micronaut and GraalVM and deploy them to Oracle Function, as I've just demonstrated. Micronaut is cloud native already and allows you to build serverless applications that are independent of your cloud platform. And it has great support for Oracle Cloud, and that it will detect that you're running an Oracle Cloud, but you can deploy Micronaut applications, same ones, to any cloud platform. You can take advantage of native image to obtain optimal cold start and memory performance, which leads to lower resource utilization and improves your cloud billing costs. Thanks very much, and it's now time for some Q&A. If there are any questions, let me know. So let's see, we have a question. What is the embedded server in Micronaut based on? Okay, so the default embedded server in Micronaut is actually based on Netty. As you saw, I changed it to Netty. However, Micronaut supports a variety of different embedded servers, including Jetty, Tomcat, the gRPC, and a whole bunch of other. The actual embedded server mechanism is completely pluggable. So, Netty is the default, but you can deploy Micronaut to a server environment as a WAR file as well. So it's actually independent of the runtime that you choose. So what are the advantages and disadvantages of just-in-time compilation versus ahead-of-time compilation? Okay, so compilation has great opportunity to optimize the application at runtime. So with the JIT, you will obtain a higher peak performance. And that's really important, particularly for applications that are long-running, because you can, over time, optimize the performance of the application and use the JIT to inline code and learn about the hot code paths and so forth. AOT doesn't have that same opportunity because it's all done ahead of time. But in the case of serverless, that's not really important because the application comes and goes. So does Micronaut support Kubernetes and Knative? Yes, Micronaut does support Kubernetes and Knative. In fact, when you create your application with Micronaut, you have the option to select features specific to Kubernetes and Knative, and what those will do will essentially just create the Kubernetes descriptors in order to ease the deployment of the application. Micronaut also has support for Kubernetes health and readiness checks, as well as Kubernetes config maps for distributed configuration, and a whole bunch of other features that make it a great fit for Kubernetes. So does Micronaut support CDI? So not currently. Micronaut currently implements the JSR 330 eject spec. However, we are working closely with the CDI community on a potential CDI Lite implementation that decouples CDI from reflection and traditional approaches that I talked about before. So hopefully in the future, Micronaut will support CDI Lite in the form that in a much reduced form, so that we don't have to support reflection and so forth.